Hello and welcome to the Sleepy Astronomer. Tonight, we're exploring our closest celestial companion through 100 carefully chosen facts. The moon that has watched over Earth for more than 4 billion years, shaping our tides, stabilizing our climate, and inspiring humanity's dreams of reaching beyond our world. If you're settling in for the first time, welcome aboard our journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Wherever you are tonight, settling in for rest or simply curious about our ancient companion, I'm so glad you're here. If this journey through lunar facts helps you unwind or fills you with quiet wonder, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. Tonight's journey unfolds as 100 discoveries about this remarkable world. Facts that become windows into larger truths about planetary formation, gravitational poetry, and humanity's relationship with the cosmos. We'll begin with the moon's basic properties, explore its violent birth and gentle influence, and discover how this ancient companion continues to shape both our planet and our imagination. Each fact we'll explore represents centuries of human observation and decades of careful measurement by astronomers around the world. From ancient civilizations tracking lunar phases to Apollo, astronauts collecting samples from another world, every piece of information about the moon has been gathered through humanity's patient study of our nearest neighbour. The moon serves as both mirror and window, reflecting our light back to us, while offering glimpses into the early history of the solar system. In studying this familiar presence that graces our night sky, we're exploring the cosmic forces that shaped our world and continue to influence life on Earth in ways both obvious and subtle. So, find your most comfortable position and let's begin our gentle journey through 100 facts that paint the portrait of Earth's ancient companion. Facts that become stories, numbers that reveal wonder, and discoveries that connect us to the cosmic dance that has been unfolding above our heads since before life began. Out there, hanging in the darkness just 384,400 kilometers away, the moon continues its patient orbit, pulling gently at our oceans, stabilizing our seasons, and casting its silver light across the same landscapes that have gazed up at its familiar face for billions of years, ready to share the secrets it has gathered during its long watch over our small blue world. Look up tonight, and there it hangs, a silver disk against the darkness, so familiar that we sometimes forget to marvel at its presence. Yet this ancient companion, suspended in the cosmic void just 384,400 kilometers above your head, represents one of the most remarkable objects in our solar system. The moon is not just Earth's satellite, it is our partner in a gravitational dance that has been unfolding for more than 4 billion years, shaping our world in ways both obvious and subtle. The moon is Earth's only natural satellite, but that simple statement barely captures the extraordinary relationship between our two worlds. Most planets in the solar system have multiple moons, or tiny captured asteroids, that barely qualify as companions. Mars has 2 small potato-shaped moons that are probably captured asteroids from the asteroid belt. Jupiter and Saturn have dozens of moons between them, but even their largest satellites are small compared to their giant parent planets. Earth's moon is different. It's enormous relative to our planet, measuring about 27% of Earth's diameter. If Earth were a basketball, the Moon would be a tennis ball sitting about 7 meters away. This size ratio is so unusual that some astronomers prefer to think of the Earth-Moon system not as a planet with a satellite, but as a double planet. The distance between Earth and Moon, that 384,400 kilometers that separates us, represents a gulf so vast that you could fit all the other planets in the solar system in the space between our worlds, with room to spare. To put this distance in perspective, if you could drive a car to the Moon at highway speeds, the journey would take more than 4 months of continuous driving. Yet in cosmic terms, this is remarkably close. The Moon is near enough that we can see features on its surface with the naked eye, close enough that it appears roughly the same size as the Sun in our sky, creating the spectacular phenomenon of total solar eclipses. This cosmic coincidence, that the Moon and Sun appear nearly identical in size from Earth's surface, is purely accidental, yet it has had profound effects on human culture and scientific understanding. The Sun is actually 400 times larger than the Moon, but it's also 400 times farther away, creating this remarkable size match in our sky. Total solar eclipses, where the Moon precisely covers the Sun's bright disk and reveals the ethereal solar corona, have inspired awe and terror throughout human history. Ancient Chinese astronomers developed sophisticated methods for predicting eclipses, believing they needed to scare away the celestial dragon devouring the Sun. Greek philosophers used eclipses to calculate the size of Earth and Moon with remarkable accuracy over 2,000 years ago. The Moon's gravitational influence reaches across that 250,000-mile gulf to orchestrate the daily rhythm of Earth's tides. Twice each day, in an endless cycle that has repeated for billions of years, our oceans rise and fall in response to the Moon's pull. This might seem like a simple, obvious process, but the tidal mechanism reveals something profound about how gravity works across vast distances and how celestial bodies can influence each other across the apparent emptiness of space. The Moon doesn't just pull on our oceans, it pulls on the solid Earth itself, causing the land beneath your feet to rise and fall by several inches twice each day, though you never notice because everything around you moves together. The same side of the Moon always faces Earth, a phenomenon called tidal locking that results from billions of years of gravitational interaction between our two worlds. This synchronous rotation means that the Moon rotates on its axis at exactly the same rate it orbits Earth, keeping one hemisphere permanently hidden from terrestrial view. This wasn't always the case. Early in the Moon's history it rotated much faster, showing all sides to Earth as it spun. But Earth's gravity gradually slowed the Moon's rotation through tidal forces, eventually locking it into the stable configuration we see today. This far side of the Moon remained a complete mystery until Soviet spacecraft first photographed it in 1959, revealing a landscape even more heavily cratered than the familiar near side. The far side looks dramatically different from the side we see, almost entirely highlands with very few of the dark maria that characterize the near side. This difference exists because Earth's gravity has influenced the Moon's internal structure over billions of years, making the crust thicker on the far side and thinner on the near side. When ancient impacts cracked the lunar crust, molten rock could more easily reach the surface on the near side, creating the dark lava plains we call maria. A day on the Moon, the time from sunrise to sunrise at any given location, lasts about 29.5 Earth days. This long day-night cycle creates temperature extremes unknown on Earth. For 2 weeks, the Sun blazes overhead in the black lunar sky, heating the surface to temperatures exceeding 120 degrees Celsius. Hot enough to boil water if any existed on the surface. Then follows 2 weeks of darkness colder than Antarctica's worst winter, with temperatures plummeting to minus 173 degrees Celsius. These extreme temperature swings occur because the Moon has virtually no atmosphere to moderate the heating and cooling effects of solar radiation. The Moon ranks as the 5th largest satellite in our solar system, larger than the planet Pluto and comparable in size to some of the smaller planets discovered around other stars. Despite its substantial size, the Moon contains only 1.2% of Earth's mass, giving it much weaker gravity. Step onto its surface, and you would weigh only 1/6 of your Earth weight. This low gravity results from the Moon's lower density. It lacks the heavy iron core that gives Earth much of its mass. An Olympic high jumper who could clear 2 meters on Earth could leap 12 meters on the Moon, soaring through the airless environment in graceful slow-motion arcs that would seem like flying. The absence of atmosphere means the lunar sky is always black, even during the 2-week-long lunar day. Without air molecules to scatter sunlight, the sky never turns blue as it does on Earth. Stars shine constantly in the Moon's sky, unblinking and unwavering without atmospheric turbulence to make them twinkle. Earth hangs in this black sky like a blue and white marble, 4 times larger than the Moon appears from Earth, slowly rotating to show the continents and oceans of the world you left behind. This view of Earth from lunar distance, Earthrise over the lunar horizon, became one of the most influential photographs ever taken when Apollo 8 astronauts captured it in 1968. Without air to scatter sunlight or provide atmospheric pressure, the Moon's surface receives the Sun's radiation directly, unfiltered by atmospheric gases. The intensity of this radiation, combined with cosmic rays from deep space and charged particles from the solar wind, makes the lunar surface a hostile environment for unprotected life. Solar radiation and cosmic particles gradually alter the composition of surface materials, creating complex organic molecules and contributing to the formation of the fine regolith that covers the Moon. Yet this same absence of atmosphere means that footprints left by Apollo astronauts may remain visible for millions of years, preserved in the fine lunar dust like fossils of humanity's first steps on another world. The Moon reflects only about 12% of the sunlight that strikes it, about the same as charcoal or worn asphalt. This low albedo results from the composition of lunar surface materials, ancient rocks and fine dust, pulverized by billions of years of meteorite impacts. The dark maria are particularly unreflective, composed of basaltic rock, similar to the volcanic rocks found in Hawaii or Iceland. Despite this low reflectivity, the Moon appears brilliant in our night sky because of its size and proximity, outshining all other celestial objects except the Sun. The leading scientific theory for the Moon's formation reads like a tale of cosmic violence transformed into beauty. About 4.5 billion years ago, when Earth was young and still forming, a Mars-sized object astronomers call Theia struck our planet in a glancing blow of unimaginable energy. This giant impact hypothesis suggests that the collision was so violent it partially vaporized both worlds, hurling massive amounts of material into orbit around Earth. The impact occurred at just the right angle, too head-on, and both worlds would have been completely destroyed, too glancing, and Theia would have bounced off into space. The collision happened when Earth was only about 50 million years old, still hot and partially molten from its own formation. Theia approached at a speed of several kilometers per second, carrying kinetic energy equivalent to billions of nuclear weapons. When the two worlds collided, the impact site briefly reached temperatures comparable to the surface of the Sun. much of both Earth and Theia was vaporized, creating a cloud of superheated rock vapor that expanded into space around the wounded Earth. Over thousands of years, this ring of molten rock and vapor gradually coalesced under its own gravity to form the Moon. The process was remarkably rapid by geological standards. Computer simulations suggest the Moon assembled from the impact debris in less than a century. Initially, the Moon was much closer to Earth than it is today, perhaps only 15,000 kilometers away, and it glowed red-hot from the heat of formation. At that distance, the Moon would have appeared 15 times larger in Earth's sky than it does today, dominating the heavens like a second, dimmer sun. This violent birth explains many of the Moon's unusual characteristics: its large size relative to Earth, its lack of a substantial iron core compared to Earth, and the striking similarity between lunar rocks and Earth's mantle. When Apollo astronauts brought back samples of lunar rock, chemical analysis revealed that the Moon's composition closely matches Earth's outer layers, exactly what you'd expect if the Moon formed from Earth's mantle material, blasted into space by a giant impact. The Moon is, quite literally, made partly from Earth itself, a piece of our world that was blasted into space and reformed as our eternal companion. The Moon's surface tells the story of the solar system's violent youth through its countless impact craters. Unlike Earth, where wind, water, and geological activity constantly reshape the landscape, the Moon preserves a record of bombardment that stretches back billions of years. Every crater represents a cosmic collision, from tiny meteorites that created pits smaller than coins to massive asteroids that excavated basins hundreds of kilometers across. The heavily cratered appearance of the Moon's highlands reveals the intensity of bombardment during the solar system's first billion years, a period astronomers call the Late Heavy Bombardment. During this violent epoch, asteroids and comets left over from planetary formation crashed into the inner planets at an incredible rate. The Moon, lacking atmosphere or geological activity to erase these scars, preserved a perfect record of this cosmic shooting gallery. Earth experienced the same bombardment, but our planet's active geology has erased most evidence of these ancient impacts. The Moon serves as Earth's memory, preserving the scars of impacts that would have been catastrophic if they occurred today. The Moon's surface is covered in a fine powder called regolith, created by eons of meteorite impacts that have pulverized surface rocks into particles finer than talcum powder. This regolith can be several meters deep in some locations, forming a layer of cosmic dust that has accumulated grain by grain over billions of years. Each impact, from microscopic meteorites to massive asteroids, contributes to this growing blanket of pulverized rock. The regolith contains microscopic glass beads formed when impacts melted rock and sprayed it across the surface, where it cooled rapidly in the vacuum of space. Apollo astronauts describe this lunar dust as clingy and abrasive, sticking to everything it touched and working its way into every crevice of their spacesuits and equipment. The dust hung in the airless environment like fog after being disturbed, taking much longer to settle than it would on Earth, because there's no air resistance to bring the particles down quickly. Some astronauts reported that the dust smelled like gunpowder when they removed their helmets, a result of chemical reactions between the dust and their life support systems. The dark patches visible to the naked eye on the Moon's surface are called maria, Latin for seas, though they contain no water. Early astronomers looking through primitive telescopes thought these smooth, dark areas might be bodies of water, hence the name that persists today. These maria were formed by ancient volcanic eruptions that filled large impact basins with molten rock between 3 and 4 billion years ago. The largest of these, Mare Imbrium, or the Sea of Rains, spans more than 1,200 kilometers and was created by an impact so massive it sent shockwaves around the entire moon and excavated material from deep in the lunar interior. The light-coloured regions between the Maria are the lunar highlands, the moon's original crust that formed when the moon was completely molten in its earliest days. These highlands are composed primarily of a rock called anorthosite, rich in the mineral feldspar, which gives them their light colour. Highland rocks are among the oldest materials in the solar system, dating back 4.4 to 4.5 billion years to the moon's formation. The highlands are heavily cratered, representing some of the oldest surfaces in the solar system and preserving a record of the intense bombardment that characterized the early solar system. The largest impact feature on the moon is the South Pole Aitken Basin, a massive crater on the far side that stretches 2,500 kilometers across, roughly the distance from New York to Denver, and penetrates up to 13 kilometers deep into the lunar crust. This ancient impact was so powerful that it may have excavated material from the moon's mantle, the layer beneath the crust, providing scientists with samples of the moon's deep interior. The basin represents one of the largest and oldest impact features in the solar system, a testament to the scale of cosmic violence in the early epochs of planetary formation. The impactor that created this basin was probably an asteroid 200 kilometers across, striking the moon with energy millions of times greater than all nuclear weapons ever built. Despite its ancient and battered appearance, the moon is not completely geologically dead. Moonquakes still occur, caused by several different mechanisms. Tidal stresses, as Earth's gravity flexes the lunar interior during the moon's elliptical orbit, generate deep moonquakes that can be felt throughout the lunar interior. Thermal moonquakes result from the expansion and contraction of surface rocks as they heat and cool during the long lunar day-night cycle. Meteorite impacts continue to shake the moon, and occasionally shallow moonquakes occur near the lunar surface for reasons that remain mysterious. These moonquakes can last up to 10 minutes, much longer than typical earthquakes, because the moon's dry, cold interior doesn't dampen seismic waves as effectively as Earth's water-rich interior. The moon's internal structure allows seismic energy to propagate much farther than it would on Earth. Apollo astronauts left seismometers on the lunar surface that detected these moonquakes and revealed something unexpected. The moon rings like a bell when struck by meteorites. The entire moon resonates for hours after a significant impact, vibrating like a struck gong in ways that Earth never does. This peculiar ringing behavior provided scientists with crucial information about the moon's internal structure. By analyzing how seismic waves travel through the moon, researchers discovered that the moon has a small iron core about 350 kilometers in radius, much smaller relative to the moon's size than Earth's core is relative to our planet. Surrounding this core is a rocky mantle similar in composition to Earth's mantle, and above that, a crust that varies in thickness from about 30 kilometers on the near side to 60 kilometers on the far side. Volcanic activity on the moon ended roughly 1 billion years ago, as the moon's small size allowed it to cool more quickly than Earth. The moon's lower mass means it retains heat less efficiently than larger planets. Heat escapes through the surface faster than it can be generated in the interior. The last volcanic eruptions filled the youngest Maria with dark basaltic lava, but since then the moon has been volcanically dormant. However, recent analysis of Apollo samples has revealed that some volcanic activity may have continued much more recently than previously thought, with some volcanic glass beads dating to as recently as 100 million years ago. The Moon once possessed a magnetic field, generated by a molten iron core similar to the mechanism that creates Earth's magnetic field today. This ancient lunar magnetic field was probably quite strong enough to deflect the solar wind and protect the lunar surface from space radiation. But as the Moon's core cooled and solidified, the magnetic dynamo shut down, and the global magnetic field disappeared about 3 billion years ago. Today, only small, localized magnetic fields remain, probably created by iron-rich rocks that were magnetized when the global field still existed. The loss of the Moon's magnetic field had profound consequences for the lunar surface environment. Without magnetic protection, the solar wind, the stream of charged particles flowing from the Sun, began striking the lunar surface directly. Over billions of years, this bombardment gradually altered the composition of surface materials, implanting hydrogen from the solar wind and contributing to complex chemical reactions that created the fine regolith layer. Perhaps most remarkably, despite the Moon's apparently dry and lifeless appearance, substantial quantities of water ice have been confirmed in permanently shadowed craters near the lunar poles. These regions never receive direct sunlight because the Moon's axis of rotation is tilted only 1.5 degrees relative to its orbit around the Sun, much less than Earth's 23.5-degree tilt that creates our seasons. This minimal tilt means that the floors of deep polar craters remain in permanent shadow, creating cold traps where temperatures stay below -230 degrees Celsius, cold enough to preserve ice for billions of years. The discovery of lunar water has been one of the most exciting developments in lunar science. NASA's L-Cross mission intentionally crashed a spent rocket stage into the shadowed Cabeus crater in 2009, then flew through the resulting debris plume to analyze its composition. The mission detected significant amounts of water vapor, along with other volatiles like carbon dioxide, methane, and even traces of silver and mercury. Subsequent missions have confirmed that these polar ice deposits are substantial and potentially accessible to future human explorers. This lunar water probably arrived through multiple sources over billions of years. Some was delivered by ancient comet impacts. These dirty snowballs from the outer solar system contained substantial amounts of ice that could have been preserved in permanently shadowed regions. The solar wind may have contributed hydrogen that combined with oxygen in lunar rocks to form water molecules. Meteorites and asteroids may have delivered additional water throughout lunar history. The presence of water ice at the lunar poles has revolutionized our thinking about the Moon's potential as a stepping stone for human expansion into the solar system. Instead of hauling all supplies from Earth at enormous cost, roughly $10,000 per kilogram just to reach low Earth orbit, future lunar colonies could potentially extract water from these polar deposits. Water can be split into hydrogen and oxygen to create rocket fuel, used directly for drinking and agriculture, or employed as radiation shielding for lunar habitats. These permanently shadowed regions represent some of the coldest places in the solar system, colder even than the surface of Pluto. The eternal darkness and frigid temperatures have created natural laboratories where scientists can study materials that have been preserved unchanged for billions of years. Future robotic missions will explore these regions in detail, mapping the extent and purity of ice deposits and searching for other volatiles that might be useful for human exploration. Recent missions have provided increasingly detailed maps of lunar water distribution. NASA's Lunar Reconnaissance Orbiter has been mapping the Moon in unprecedented detail since 2009, using neutron detectors to identify hydrogen signatures that indicate the presence of water ice. China's Chang'e missions have provided ground truth measurements from the lunar surface, while India's Chandrayaan missions have contributed additional orbital observations. This growing database of lunar water information is crucial for planning future human missions to the Moon. As we gaze up at this ancient companion tonight, we see not just a distant world of craters and dust, but Earth's partner in a cosmic dance that began with violence and has evolved into the stable relationship that makes complex life possible on our planet. The Moon's story is inseparable from Earth's story, from the cataclysmic impact that created it to the gentle gravitational embrace that continues to shape both worlds. In studying our nearest neighbour, we learn not just about the Moon itself, but about the forces that shaped our entire solar system and continue to influence our planet today. The Moon pulls at Earth with invisible hands across 384,400 kilometres of empty space, orchestrating a gravitational ballet that has been unfolding for more than 4 billion years. This cosmic dance between our two worlds shapes everything from the rhythm of ocean tides to the very length of our days, creating the stable conditions that allowed complex life to flourish on our planet. Twice each day, in an endless cycle that has repeated for billions of years, our oceans rise and fall in response to the Moon's gentle pull. But the tidal mechanism reveals something more profound than water, simply following the Moon around Earth. The Moon doesn't just pull on our oceans, it pulls on the entire planet, creating two tidal bulges, one facing the Moon and one on the opposite side. This cosmic breathing gives us two high tides approximately every 24 hours and 50 minutes, a rhythm that has become the heartbeat of coastal life. The solid earth beneath your feet participates in this gravitational dance, rising and falling by about 30 centimeters twice each day. You never notice because everything around you, buildings, trees, the ground itself, moves together in this gentle planetary breathing. The solid earth tide is actually stronger than ocean tides in terms of the forces involved, but water flows more easily than a rock, making ocean tides more visible to our eyes. Without the Moon's stabilizing influence, Earth would wobble chaotically on its axis, like a spinning top running down. The Moon's gravitational pull keeps Earth's axial tilt steady at about 23.5 degrees, preventing extreme climate changes that would make complex life nearly impossible. Computer simulations reveal that without our lunar companion, Earth's tilt could vary from nearly 0 degrees to more than 85 degrees over periods of millions of years. Such dramatic changes would create climate chaos, ice ages and furnace periods, alternating unpredictably, making it nearly impossible for life to adapt and evolve. The Moon serves as Earth's cosmic anchor, maintaining the stable seasons that have allowed life to flourish for billions of years. Our familiar cycle of spring, summer, autumn and winter exists because the Moon keeps Earth's tilt steady. Mars, which lacks a large stabilizing moon, experiences dramatic changes in its axial tilt over geological time, contributing to its harsh and variable climate. Earth's remarkable climate stability, the narrow range of temperatures that keeps water liquid over most of our planet, depends in part on the Moon's gravitational embrace. The gravitational dance between Earth and Moon has been slowing our planet's rotation since the Moon first formed, writing the story of time itself in the rhythm of tides and the length of days. In Earth's youth, when the Moon hung much closer to our world, perhaps only 15,000 kilometers away, compared to today's 384,400, days lasted only about 6 hours. Our planet spun like a cosmic top, racing through day-night cycles while the enormous Moon dominated the sky, appearing 15 times larger than it does today. Imagine standing on that ancient Earth watching a moon so massive it filled nearly a quarter of the sky, its red-hot surface glowing like a second sun. The tides in those early days were not the gentle risings we know today, but massive walls of water hundreds of meters high, reshaping coastlines with every passage. The gravitational forces were so intense that Earth itself flexed and bulged dramatically, generating enormous amounts of heat through tidal friction that may have kept our planet's surface molten for millions of years longer than it would have remained otherwise. The tidal forces that create our modern ocean tides also act as a cosmic brake on Earth's rotation, a mechanism of such elegant physics that it transforms the kinetic energy of our spinning planet into orbital motion of the moon. This energy doesn't vanish, it flows across the vacuum of space through gravitational interaction, causing our satellite to spiral outward at about 3.8 centimeters per year. This is roughly the rate at which your fingernails grow, a cosmic process so gradual that it takes sophisticated laser measurements to detect, yet so relentless that it has been reshaping our world for billions of years. This recession continues today, measurable by laser reflectors left on the lunar surface by Apollo astronauts. Scientists fire laser pulses at these reflectors and measure the time it takes for light to return, tracking the moon's distance with millimeter precision. Each year, the moon drifts slightly farther from Earth, and each year, our days grow slightly longer by about 1.7 milliseconds per century. This seems insignificant, but over geological time it adds up to dramatic changes in both the Earth-Moon system and the conditions for life on our planet. The moon's gradual retreat means that total solar eclipses, one of nature's most spectacular phenomena, are temporary in cosmic terms. Currently, the moon appears almost exactly the same size as the sun in Earth's sky, a cosmic coincidence that creates the breathtaking experience of totality. The sun is about 400 times larger than the moon, but it's also about 400 times farther away, creating this remarkable size match that allows the moon to precisely cover the sun's bright disk during total solar eclipses. This perfect size relationship is purely accidental, yet it has profoundly influenced human culture and scientific understanding. Ancient astronomers used eclipses to calculate the size of Earth and Moon with remarkable accuracy. The Greek philosopher Aristarchus used eclipse observations to estimate the relative distances to the Sun and Moon over 2,000 years ago, laying the groundwork for understanding our place in the cosmos. This cosmic coincidence won't last forever, adding poignancy to every total solar eclipse we witness today. As the Moon continues its slow recession, growing smaller in our sky with each passing millennium, it will eventually be unable to completely cover the Sun's disk. In about 600 million years, a span of time that encompasses the entire evolution of complex life on Earth, the Moon will be too distant to create total solar eclipses. Future generations of Earth's inhabitants, whatever form they might take, will never experience the ethereal beauty of the solar corona revealed during totality, when day becomes night in minutes and stars appear in the afternoon sky. Consider the cosmic timing that allows us to witness total solar eclipses today. Earth has existed for 4.5 billion years and will likely remain habitable for another billion years before the sun's increasing brightness makes our planet too hot for liquid water. In this vast span of time, the window for perfect total solar eclipses, when the moon appears exactly the right size to cover the sun, is relatively brief, perhaps 100 million years centered on our current epoch. We live during the brief cosmic moment when these spectacular alignments are possible, a coincidence that seems almost too perfect to be accidental. The eclipse experience itself demonstrates the exquisite precision of celestial mechanics. During totality, temperatures can drop by 10 to 15 degrees Celsius within minutes, as the moon's shadow blocks the sun's heat. Winds change direction, often reversing completely as the shadow approaches and passes. Animals exhibit behavior typically seen at dusk. Birds return to their roosts with confused chirping. Crickets begin their evening songs in the middle of the day, and flowers may close their petals as if night has fallen. Domestic animals often show signs of anxiety or confusion, sensing that something fundamental about their world has changed. The moon's shadow races across Earth's surface at speeds that can exceed 2,000 kilometers per hour, faster than any supersonic aircraft. This shadow, the umbra, creates the path of totality, typically only 200 to 300 kilometers wide. The experience of totality itself can last from a few seconds to about 7 minutes, depending on the observer's location relative to the moon's orbit and Earth's rotation. Those precious minutes of totality reveal the sun's corona, a shimmering crown of superheated plasma extending millions of kilometers into space, normally invisible due to the overwhelming brightness of the solar disk. The path of totality, the narrow band where observers can see the sun completely blocked, is typically only about 200 kilometers wide. Outside this path, observers see a partial eclipse, where the moon covers only part of the sun. The difference between seeing a partial eclipse and a total eclipse is like the difference between being caught in a rainstorm and being struck by lightning. Both involve the same celestial mechanics, but the experience is utterly different. Lunar eclipses offer a different kind of celestial theatre, revealing Earth's cosmic shadow projected across the face of our satellite. When Earth passes between the sun and moon, our planet's shadow engulfs the lunar surface, but rather than disappearing completely, the moon transforms into a glowing orb of deep copper red. This blood moon phenomenon occurs because Earth's atmosphere acts like a lens, bending sunlight around our planet's edges and filtering out blue wavelengths while allowing red light to pass through. The same atmospheric scattering that paints our sunsets in shades of orange and crimson creates the moon's reddish glow during eclipse. Imagine all the sunrises and sunsets occurring around Earth's rim at the moment of lunar eclipse. Their combined light, filtered through thousands of kilometers of atmosphere, illuminates the moon with the warm glow of all Earth's twilight hours occurring simultaneously. The intensity of this red color varies with atmospheric conditions. Volcanic eruptions or dust storms can make eclipsed moons appear darker and more ominous, while clear atmospheric conditions create brighter, more copper-colored eclipses. Ancient civilizations often interpreted lunar eclipses as omens of catastrophic change, and it's easy to understand why. The sight of the familiar silver moon transforming into a blood-red disk hanging in the night sky must have seemed deeply unnatural to observers who lacked understanding of celestial mechanics. Many cultures developed elaborate myths to explain these events. Chinese astronomers believed a celestial dragon was devouring the moon, requiring loud noises and bright lights to scare the beast away. The ancient Greeks thought lunar eclipses resulted from witchcraft or divine displeasure, while Inca astronomers believed a jaguar was eating the moon. Despite their mythological explanations, many ancient astronomers achieved remarkable accuracy in predicting eclipses. The Babylonians developed sophisticated mathematical methods for calculating eclipse cycles based on careful observations spanning centuries. They discovered the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours, after which eclipses repeat in nearly identical patterns. This discovery allowed them to predict eclipses decades in advance, a capability that seemed almost supernatural to their contemporaries and elevated the status of astronomer priests who jealously guarded this knowledge. The moon's influence on Earth extends far beyond tides and eclipses, reaching into every aspect of our planet's systems with a subtlety that scientists are still discovering. The lunar gravitational pull may have played a crucial role in stirring Earth's early oceans, creating currents and mixing patterns that distributed nutrients and chemical building blocks necessary for life's emergence. Some researchers theorize that tidal pools, those shallow coastal areas alternately covered and exposed by lunar tides, provided ideal laboratory conditions for the complex chemistry that eventually led to self-replicating molecules and the first primitive life forms. These tidal zones create unique environments where water repeatedly concentrates and dilutes, where materials from land and sea mix and separate in regular cycles, and where the energy of moving water drives chemical reactions that might not occur in static conditions. The alternating wet and dry conditions in tidal pools could have facilitated the formation of cell membranes, the concentration of organic molecules, and the development of the first crude metabolic processes. In this sense, the moon may have served as midwife to life itself, providing the rhythmic environmental changes that nudged chemistry toward biology. The moon also affects Earth's atmosphere in ways both subtle and measurable, creating atmospheric tides that mirror the more familiar ocean tides. These atmospheric tides cause regular variations in air pressure, typically only a few millibars, but they're detectable with sensitive instruments and can influence weather patterns over long time scales. The moon's gravitational pull stretches Earth's atmosphere just as it stretches our oceans, creating pressure waves that circle the globe every lunar day. Meteorologists have discovered correlations between lunar phases and certain weather phenomena, though the mechanisms remain complex and sometimes controversial. Some studies suggest that atmospheric tides may influence storm formation and precipitation patterns, particularly in tropical regions where other atmospheric effects are relatively weak. While these lunar influences on weather are small compared to solar heating and other meteorological forces, they demonstrate how thoroughly the moon's presence permeates every aspect of our planet's behavior. Spring tides and neap tides reveal the elegant mathematical relationship between Earth, Moon, and Sun as they perform their gravitational choreography. Spring tides occur twice each month during new and full moon phases, when the three celestial bodies align and combine their gravitational pulls to create especially dramatic tidal ranges. The name spring doesn't refer to the season, but to the way water seems to spring higher up beaches and farther into estuaries during these alignments. Neap tides occur during the moon's first and third quarter phases, when the sun and moon are positioned at right angles relative to Earth. In this configuration, the solar tide partially cancels the lunar tide, creating more moderate tidal ranges. The word neap comes from an Old English term meaning without the power of advancing, describing how these tides seem restrained compared to their spring counterparts. This regular alternation between spring and neap tides creates a complex rhythm that marine life has learned to exploit over millions of years of evolution. Supermoons, when the full moon coincides with the moon's closest approach to Earth in its elliptical orbit, creates slightly stronger tides than usual. The difference is small, typically increasing tidal ranges by only a few centimeters, but it demonstrates how even minor variations in the moon's distance can influence our planet. The moon's orbit is not a perfect circle, but an ellipse, bringing it as close as 356,500 kilometers and as far as 406,700 kilometers from Earth. The Moon's gravitational influence has also helped shape the evolution of life on Earth in more direct ways. Many marine organisms time their reproductive cycles to lunar phases, releasing eggs and sperm during specific tidal conditions that maximize the chances of successful fertilization and dispersal. Coral reefs around the world spawn in coordinated events timed to lunar cycles, creating underwater blizzards of reproductive material that ensure genetic diversity and species survival. Even terrestrial animals show lunar influences in their behavior. Many nocturnal predators hunt more successfully during new moon phases when darkness provides better cover. Some bird species migrate during specific lunar phases, possibly using the moon's light for navigation. Marine turtles return to their birth beaches to nest during high tides, often guided by lunar cycles embedded in their genetic programming. The moon serves as Earth's shield as well as its dance partner. Its substantial gravitational field deflects some asteroids and comets that might otherwise strike our planet, while Earth's larger gravity well attracts more potentially dangerous objects. The moon's presence creates a more complex gravitational environment that can alter the trajectories of incoming cosmic debris. Some objects that might have hit Earth instead impact the moon, where they create new craters but pose no threat to terrestrial life. This protective effect is subtle but significant over geological timescales. The heavily cratered lunar surface preserves evidence of the cosmic bombardment that both worlds experienced during the solar system's violent youth. Each lunar crater represents a potential impact that might have struck Earth instead, possibly altering the course of evolution, or even preventing the development of complex life. The moon's role as cosmic timekeeper extends beyond its influence on tides and day length. Lunar phases provided humanity's first reliable calendar, creating the concept of the month, originally a moonth, that still organizes our lives today. Before artificial lighting, the moon's changing face marked the passage of time more clearly than any other celestial phenomenon. Agricultural societies planned planting and harvesting around lunar cycles, and many traditional festivals still follow lunar calendars. The gravitational relationship between Earth and Moon also demonstrates one of physics' most elegant principles, the conservation of angular momentum. This fundamental law states that the total rotational energy in a system remains constant unless acted upon by external forces. As tidal friction slows Earth's rotation, that lost rotational energy doesn't simply vanish. It transfers across 384,400 kilometers of vacuum to increase the Moon's orbital energy, causing our satellite to spiral outward. This cosmic accounting system keeps perfect books, with every minute of Earth day lengthening, precisely balanced by a corresponding increase in the Moon's orbital distance. The mathematical beauty of this process reveals itself in precise measurements taken over decades. Using laser reflectors placed on the lunar surface by Apollo astronauts, scientists can measure the Moon's distance to within millimeters. These lunar laser ranging experiments confirm that the Moon recedes by exactly the amount predicted by tidal theory, providing one of the most precise confirmations of gravitational physics ever achieved. The Moon's retreat rate varies slightly due to changes in Earth's ice sheets, ocean currents, and even atmospheric pressure, but the overall trend remains remarkably consistent. This gradual recession means that ancient eclipses provide a unique window into Earth's rotational history. By calculating when and where historical eclipses occurred, and comparing those predictions with ancient records, scientists can determine how much Earth's rotation has slowed over recorded history. Chinese astronomers recorded solar eclipses with impressive accuracy for over 2,000 years, creating an invaluable data set for studying long-term changes in Earth rotation. These historical eclipse records reveal that Earth's rotation rate has not been perfectly uniform. Ice ages, continental drift, and other geological processes have caused slight variations in day length over millennia. Eventually, this gravitational dance will reach a state of equilibrium called mutual tidal locking, where both Earth and Moon always show the same face to each other. In this distant future, Earth days will equal lunar months, both lasting about 47 current Earth days. The Moon will hang motionless in the sky over one hemisphere of Earth, never rising or setting, while the other hemisphere will experience eternal lunar night, never seeing our satellite at all. The contrast between these two hemispheres will be profound, one side living under permanent moonlight, the other knowing the Moon only as a theoretical concept. But this transformation will require tens of billions of years to complete, far longer than the Sun is expected to remain stable. Long before mutual tidal locking occurs, our star will evolve into a red giant, expanding to engulf Earth's current orbit. The Earth-Moon system, if it survives at all, will exist in a dramatically different environment where the rules of habitability will have changed completely. In cosmic terms, we live during the early chapters of the Earth-Moon gravitational story, witnessing a dance that has barely begun despite its already ancient history. The Moon's gradual recession also affects the stability of Earth's rotation in ways that scientists are still investigating. While the Moon currently stabilizes Earth's axial tilt, preventing the chaotic climate variations that Mars experiences, this stabilizing influence will weaken as our satellite moves farther away. Computer models suggest that in the far future, as the Moon's stabilizing effect diminishes, Earth may begin to experience larger variations in axial tilt, potentially triggering dramatic climate changes. However, these shifts will occur over timescales so vast that they're largely academic. The Sun's evolution will likely render Earth uninhabitable long before lunar recession destabilizes our planet's rotation. Mars provides a sobering example of what Earth might be like without a large, stabilizing moon. The red planet's axial tilt varies chaotically between 15 and 35 degrees over periods of millions of years, causing dramatic climate shifts that may explain why Mars appears to have lost most of its atmosphere and surface water. When Mars tilts more severely, its polar ice caps can sublime completely, releasing enormous amounts of water vapor and carbon dioxide into the atmosphere before refreezing when the tilt decreases again. Earth's stable 23.5-degree tilt maintained by lunar gravity has allowed our planet to avoid such dramatic climate oscillations, preserving the stable conditions necessary for complex life to evolve and flourish. This cosmic dance between Earth and Moon, this gravitational embrace across nearly 400,000 kilometers of space, continues above our heads every moment, shaping our world in ways both obvious and subtle. The tides that wash our shores, the length of our days, the stability of our seasons, and even the possibility of the life that contemplates these relationships all depend on the invisible threads of gravity that bind our world to its ancient companion. As the Moon drifts slowly outward through the night sky, it carries with it the energy of Earth's rotation, gradually transforming both worlds through the patient alchemy of gravitational forces. This is the cosmic dance that has been unfolding since our satellite's violent birth, a dance that will continue long after the last human has looked up to wonder at the silver disk, hanging in the darkness above. The Moon waited patiently for 4.5 billion years before the first visitors arrived from the blue world hanging in its black sky. When humanity finally reached across the 250,000-mile gulf that separates Earth from its ancient companion, we left more than footprints in the fine lunar dust. We left evidence of a species that had learned to slip the bonds of gravity and touch another world with curious hands and wondering eyes. The journey to the moon began not with rockets, but with dreams reflected in the night sky. Every civilization that has gazed upward has wondered about that silver disk, weaving stories and myths around its changing face. The ancient Greeks imagined Artemis racing her chariot across the heavens. Chinese legends spoke of Chang'e, the moon goddess who lived in a palace among the lunar mountains with only a jade rabbit for company. Hindu texts described the moon as Chandra, riding through the cosmos in a chariot pulled by white horses. These weren't primitive superstitions, but humanity's first attempts to understand our cosmic neighborhood through the language of story and symbol. But it was the 20th century that transformed lunar mythology into engineering reality, when the patient mathematics of orbital mechanics replaced the poetry of legend. The space race that captured the world's imagination began not with noble dreams of exploration, but with the stark realities of Cold War competition. Two superpowers discovered that the rockets capable of hurling nuclear weapons across continents could also lift human beings beyond Earth's atmosphere, and perhaps even to the moon itself. The Soviet Union struck first in this cosmic competition, launching Lunar 2 in September 1959, the first human-made object to reach the moon. This small probe, weighing just 390 kilograms, carried no scientific instruments, only metal pennants bearing the Soviet coat of arms and the date of launch. Its impact near the Mare Serenitatis on September 14, 1959, marked a profound moment in human history that reverberated far beyond Cold War politics. For the first time, something created by human hands had travelled across the vast gulf of space to touch another world. The achievement was both symbolic and practical, proving that the same rocket technology capable of delivering nuclear weapons across continents could also propel objects beyond Earth's gravitational embrace. Lunar 2's journey took 36 hours, during which it travelled 384,400 kilometres through the vacuum of space at speeds approaching 11 kilometres per second. The probe carried instruments to measure magnetic fields and radiation during its brief flight, but its primary mission was simply to arrive, to demonstrate that the moon was not an unreachable destination, but a place where human technology could venture. The impact itself released energy equivalent to about 100 kilograms of TNT, creating a small crater in the ancient lunar soil and scattering Soviet pennants across a landscape that had remained undisturbed for millions of years. Radio contact with Lunar 2 ceased abruptly at the moment of impact, but the silence itself confirmed success. Somewhere in the Sea of Serenity, metallic fragments bearing the hammer and sickle lay scattered across regolith that had been accumulating grain by grain since the solar system's formation. Lunar 3, launched just weeks later, provided humanity's first glimpse of the moon's far side, the hemisphere that had remained hidden throughout all of human history. The grainy, black and white photographs revealed a landscape even more heavily cratered than the familiar near side, with almost no dark maria to soften the ancient scars. This hidden face of the moon looked alien and forbidding, a cosmic battlefield that had absorbed billions of years of asteroid and comet impacts without the geological activity that might have healed the wounds. The lunar far side appears so different from the near side because Earth's gravity has influenced the moon's internal structure over geological time. The crust is thicker on the far side, up to 60 kilometers in some places compared to 30 kilometers on the near side. When ancient impacts cracked the lunar crust, molten rock could more easily reach the surface on the near side, creating the dark lava plains we call maria. The far side, with its thicker crust, remained largely a highland wilderness of ancient impact craters. These early robotic missions revealed the Moon as a world of extremes that would challenge every aspect of human space exploration. Temperatures ranged from 120 degrees Celsius in direct sunlight, hot enough to melt lead, to minus 173 degrees Celsius in shadow, creating thermal stresses that could shatter metal components and turn flexible materials brittle as glass. The 14-day lunar day, followed by 14 days of darkness, created a thermal environment unlike anything on Earth, where temperature differences of nearly 300 degrees Celsius occurred across distances measured in meters. The lunar surface lay buried under meters of fine regolith created by billions of years of meteorite bombardment, a powder so fine that individual grains measured only 40 to 800 micrometers, finer than talcum powder and far more abrasive. This regolith possessed an almost electrostatic quality in the vacuum environment, clinging to everything it touched and penetrating the smallest gaps in equipment. The dust particles, shaped by eons of micrometeorite impacts rather than wind and water erosion, were sharp and angular, capable of abrading metals and clogging delicate mechanisms. And hanging over everything was the reality of hard vacuum, an environment where unprotected humans would lose consciousness within 15 seconds and die within 2 minutes. The absence of atmospheric pressure meant that water would instantly boil away, while the lack of oxygen would render any air-breathing life form helpless. Solar radiation and cosmic rays, normally filtered by Earth's atmosphere and magnetic field, bombarded the lunar surface with intensities that could prove lethal to unprotected life within hours. The Moon's gravity, only 1/6 that of Earth, created opportunities and challenges in equal measure, while the reduced gravitational pull would allow humans to perform feats impossible on Earth, jumping several meters high and carrying equipment that would be impossibly heavy at home. It also meant that familiar activities like walking, climbing, and working with tools would require completely new techniques. The absence of atmospheric resistance meant that dropped objects would fall in perfect parabolic arcs, but dust kicked up by footsteps would hang in the vacuum much longer than intuition suggested. Yet these harsh realities only intensified the challenge that President John F. Kennedy laid before the American people on May 25, 1961. I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the Moon and returning him safely to the Earth. The audacity of this declaration becomes clear when you consider that, at the time Kennedy spoke these words, the United States had managed exactly 15 minutes of human spaceflight experience, Alan Shepard's brief suborbital hop 3 weeks earlier. The Apollo program that emerged from Kennedy's challenge represented one of the largest technological undertakings in human history, employing more than 400,000 people across thousands of companies and universities, consuming roughly 4% of the federal budget at its peak, about $25 billion in 1970s dollars, equivalent to over $150 billion today. The program's scope encompassed everything from developing new materials capable of withstanding the thermal extremes of space, to creating navigation systems that could guide spacecraft across hundreds of thousands of kilometers with pinpoint accuracy. The Saturn V rocket, developed to carry astronauts to the Moon, stood 111 meters tall, taller than the Statue of Liberty, and weighed 2.8 million kilograms when fully fueled with liquid oxygen and kerosene. This mobile skyscraper was designed for a single purpose: to escape Earth's gravitational embrace and hurl 45 tons of spacecraft toward the Moon. Its first stage alone contained 5 F-1 engines, each one capable of generating 6.8 million newtons of thrust, burning fuel at a rate of nearly 3,000 kilograms per second. The sound of a Saturn V launch defied human experience. The acoustic energy generated by the 5 F-1 engines created a roar that could be heard 160 kilometers away and registered on seismographs as artificial earthquakes. At the launch pad, the sound reached 220 decibels, intense enough to kill anyone standing too close. The acoustic waves reflected off the ground, and nearby structures created a cacophony so violent that it could crack concrete and shatter windows kilometers away. Photographers covering launches had to position their cameras far from the pad and triggered them remotely, because the sound would arrive long after the light. The engineering challenges of the Saturn V pushed 1960s technology to its absolute limits. The rocket's guidance computer contained less processing power than a modern pocket calculator, yet it had to calculate trajectories across the solar system and perform complex orbital maneuvers with mathematical precision. The fuel pumps in the first stage moved liquid oxygen at rates equivalent to draining an average swimming pool in 25 seconds. The rocket's structure had to be strong enough to support its own enormous weight, while remaining light enough to achieve the velocities necessary for lunar missions. Each Saturn V launch consumed resources on an almost incomprehensible scale. The 2,100 tons of liquid oxygen and rocket-grade kerosene in the first stage alone cost more than $200,000 in the 1960s money. The entire rocket, including its Apollo spacecraft payload, represented an investment of approximately $400 million per launch, enough to fund a major university for decades. Yet this massive expenditure bought something priceless: the capability to transport 3 human beings and their life support systems across the cosmic gulf to another world. The complexity of the Apollo spacecraft defied easy comprehension. The command module that housed 3 astronauts contained more than 2 million individual parts, each one representing a potential point of failure that could doom the mission. The lunar module, the fragile-looking craft that would actually land on the Moon, was perhaps the most specialized vehicle ever built, designed for a single purpose in an environment where no help would be available if something went wrong. Apollo 8 provided humanity's first direct view of Earth from lunar distance in December 1968, during a flight that carried 3 astronauts around the Moon's far side for the first time. When their spacecraft emerged from behind the Moon, the crew witnessed something no human had ever seen: Earth rising over the lunar horizon like a blue and white marble suspended in the cosmic void. The photograph they captured, Earthrise, became one of the most influential images ever taken, showing our planet as it truly is: a small, fragile oasis of life in an otherwise hostile universe. The philosophical impact of seeing Earth from lunar distance proved as profound as the technological achievement of getting there. Astronaut William Anders, who took the Earthrise photograph, later reflected that they had come to explore the Moon but instead discovered Earth. From lunar distance, national boundaries disappeared, weather patterns became visible, and the planet's atmosphere appeared as a gossamer thin shell barely protecting the complex web of life beneath. The environmental movement that emerged in the 1970s drew much of its inspiration from these images of Earth's isolation and fragility. Apollo 11's landing in the Sea of Tranquility on July 20th, 1969, marked the culmination of humanity's longest journey, but the final moments of descent nearly ended in disaster. As Neil Armstrong and Buzz Aldrin guided their lunar module toward the surface, alarms began sounding in their cramped cockpit. The computer was overloaded, struggling to process navigation data while simultaneously running the guidance program. Program 1202 and 1201 alarms, codes that meant the computer was receiving more tasks than it could handle, flashed repeatedly as the surface approached. With fuel running critically low, less than 30 seconds remaining, Armstrong took manual control of the lunar module and flew it like a helicopter over a boulder field that threatened to destroy the fragile craft. The lunar module, designed for the vacuum of space rather than atmospheric flight, handled like nothing Armstrong had ever flown. Without air resistance or aerodynamic controls, every movement required precise thruster burns that consumed precious fuel. Through his triangular window, Armstrong could see the lunar surface approaching with a startling clarity. The lack of atmospheric haze made distances deceptive. Craters that appeared close enough to touch were actually kilometers away, while rocks the size of automobiles looked like pebbles until the last moments before landing. The surface itself seemed to rush upward as the lunar module descended, kicking up clouds of fine dust that obscured landmarks and made depth perception nearly impossible. When the Eagle finally touched down with a gentle bump, contact light, Armstrong shut down the descent engine with fuel remaining for perhaps 20 seconds of flight. The landing site, later named Tranquility Base, lay about 6 kilometers from the originally planned target, but it might as well have been in another solar system for the achievement it represented. 2 human beings now sat on the surface of another world, 384,400 kilometers from home, having completed a journey that began with Kennedy's challenge 8 years earlier. The experience of walking on the moon proved both familiar and utterly alien to the 12 men who made the journey between 1969 and 1972. The lower gravity, 1/6 of Earth's, allowed the astronauts to move in ways impossible on their home planet, taking bounding steps that carried them several meters with each stride. Eugene Cernan, commander of Apollo 17, described the sensation as similar to being on a trampoline, where each step launched him higher and farther than earthly experience suggested possible. The peculiar physics of lunar locomotion required new techniques that no amount of Earth-based training could fully prepare astronauts for. Running became a series of long, floating leaps. Jumping straight up could propel an astronaut 2 meters into the airless sky. But the lack of air resistance also meant that recovery from stumbles took longer. Without atmospheric drag to slow rotation, an astronaut who began to tumble would continue spinning until something stopped them. The 80-kilogram life support backpacks that each astronaut carried shifted their center of gravity, making balance more challenging despite the reduced weight. The absence of atmosphere meant that objects fell with perfect mathematical precision, unaffected by air resistance or atmospheric turbulence. During Apollo 15, Commander David Scott demonstrated Galileo's theories about gravity in the most dramatic possible setting, simultaneously dropping a hammer and falcon feather. Without air to create different rates of fall, both objects struck the lunar surface at exactly the same instant, confirming what Italian physicists had theorized 4 centuries earlier about the nature of gravitational acceleration. But the moon's alien nature asserted itself in countless subtle ways. The fine regolith that covered everything proved clingy and abrasive, working its way into every crevice of spacesuits and equipment. The dust hung in the airless environment like fog after being disturbed, taking much longer to settle than it would on Earth. Some astronauts reported that the dust smelled like gunpowder when they removed their helmets, a result of chemical reactions between lunar minerals and their life support systems. The landscape itself challenged earthly expectations at every turn. Without atmospheric haze to provide visual cues about distance, objects that appeared close might be kilometers away, while nearby rocks seemed impossibly sharp and clear. The black sky never changed. Whether viewed at lunar noon or midnight, stars shone constantly alongside an unfiltered sun that blazed white-hot in the airless environment. Earth hung overhead like a blue and white beacon, 4 times larger than the moon appears from Earth, slowly rotating to show the continents and weather patterns of the world the astronauts had left behind. Each Apollo mission brought back samples of lunar rock and soil that proved to be among the most valuable scientific specimens ever collected. These 382 kilograms of lunar material, carefully catalogued and preserved in special nitrogen-filled chambers at Johnson Space Center, represent 4.5 billion-year-old pieces of the early solar system, pristine samples that have never been contaminated by Earth's atmosphere, water, or life. The meticulous care taken to preserve these samples reflects their irreplaceable scientific value. They are the only materials from another world that humans have successfully brought home. The sample collection process itself required extraordinary precision and planning. Astronauts trained for months to recognize different types of lunar rocks and to document their findings with photographs and detailed written descriptions. Each sample had to be photographed in place before collection, with additional images showing its relationship to surrounding terrain. The astronauts used specially designed tongs, scoops, and core tubes to gather materials without contaminating them with human skin oils or Earth-based materials from their spacesuits. The sample containers, made of aluminum and sealed with indium gaskets, were designed to maintain the vacuum of space during the journey home. This preservation of the lunar environment proved crucial for later analysis, as many of the most important discoveries came from studying how solar wind particles had implanted themselves in lunar soil grains. These microscopic samples of the solar wind, preserved in lunar regolith for billions of years, provided scientists with a record of how the sun's behavior had changed over geological time. Analysis of Apollo samples confirmed the giant impact hypothesis for the moon's formation and revealed profound insights about the early solar system. The rocks contained no water, no organic compounds, and no signs that life had ever existed on the moon. But they told an even more remarkable story about cosmic violence and planetary formation. The isotopic composition of lunar rocks matched Earth's mantle with stunning precision, providing chemical fingerprint evidence that the moon had indeed formed from terrestrial material blasted into space by an ancient collision. The oldest samples, pieces of the primordial crust that formed when the moon was completely molten, date back 4.5 billion years, making them among the oldest materials in the solar system. These anorthosite rocks, rich in the mineral feldspar, tell the story of the moon's early differentiation through a process called the lunar magma ocean. When the moon first formed, it was entirely molten to a depth of hundreds of kilometers. As this global ocean of magma slowly cooled over millions of years, denser materials like olivine and pyroxene crystallized first and sank toward the bottom, while lighter feldspar crystals floated to the surface like mineral foam. This process of differentiation created the lunar highlands, the light-colored, heavily cratered regions that dominate the moon's far side and much of the near side. These highland rocks represent some of the moon's original crust, a record of planetary formation preserved in a world that lacks the geological activity that would have destroyed such ancient materials on Earth. When astronauts collected samples of these rocks, they were literally holding pieces of the moon's birth certificate in their gloved hands. The dark Maria, by contrast, formed much later in lunar history when massive asteroid impacts cracked the thick highland crust and allowed molten rock from the moon's interior to flow onto the surface. Apollo samples from the Maria consist primarily of basalt, dark, dense volcanic rock similar to what forms at mid-ocean ridges on Earth. But lunar basalts differ from terrestrial volcanic rocks in crucial ways that reveal the moon's unique history and composition. Lunar basalts contain high concentrations of titanium, giving them a distinctive dark color and unusual density. Some mere basalts contain titanium concentrations 10 times higher than typical Earth basalts, suggesting that the moon's interior chemistry differs significantly from our planet's. These rocks also show signs of formation in an extremely dry environment. They contain virtually no water-bearing minerals and show evidence of having crystallized from magmas that were completely anhydrous. Perhaps most remarkably, lunar samples revealed the presence of materials that could only have formed in the vacuum of space. Solar wind particles, primarily hydrogen, helium, and heavier elements from the sun, had been implanted in lunar soil grains for billions of years, creating microscopic time capsules that preserved a record of solar activity throughout much of the solar system's history. These implanted particles proved that the moon had indeed been exposed to space for its entire existence, never possessing a substantial atmosphere that might have shielded its surface from solar radiation. The Apollo missions also left behind scientific instruments that continued to function long after the astronauts returned to Earth, transforming the moon into humanity's first permanent scientific outpost. Seismometers placed on the lunar surface by Apollo crews detected thousands of moonquakes and revealed the moon's internal structure through analysis of how seismic waves traveled through the lunar interior. These instruments operated for years, powered by radioisotope thermoelectric generators that converted the heat from radioactive decay into electricity. The seismic data revealed that the moon has a small iron core about 350 kilometers in radius, much smaller relative to the moon's size than Earth's core is relative to our planet. Surrounding this core is a rocky mantle similar in composition to Earth's mantle, and above that, a crust that varies dramatically in thickness from about 30 kilometers on the near side to 60 kilometers on the far side. This asymmetry in crustal thickness helps explain why the near and far sides of the moon look so different from each other. Laser reflectors installed by Apollo crews created an even more enduring scientific legacy. These simple devices, arrays of corner cube reflectors that bounce light directly back toward its source, still function perfectly more than half a century after their installation. Scientists around the world routinely fire laser pulses at these reflectors and measure the time it takes for light to return, allowing them to track the moon's distance with millimeter precision. This lunar laser ranging has confirmed Einstein's theories about gravity, detected tiny variations in the moon's orbit, and tracked the moon's gradual recession with unprecedented accuracy. These passive experiments continue to provide valuable data more than 50 years after their installation, testament to the enduring scientific value of human presence on other worlds. Unlike robotic missions that eventually cease to function when their power sources fail or their instruments break down, the reflectors left by Apollo astronauts will continue to serve science for as long as humans are capable of firing lasers at the moon, potentially for thousands of years into the future. The end of the Apollo program in 1972 marked not just the conclusion of a technological achievement, but the close of humanity's first chapter as a spacefaring species. For the first time in human history, we had gained the ability to leave Earth and survive on another world, however briefly. The footprints left in lunar regolith by 12 astronauts will remain visible for millions of years, preserved in the airless environment like fossilized evidence of our first tentative steps into the cosmic ocean. Between Apollo and the modern era of lunar exploration lies a gap of decades, during which the Moon seemed almost forgotten by the space agencies that had once competed so fiercely to reach it. But robotic missions continue to expand our understanding of lunar science and prepare for humanity's eventual return. Japan's Selene mission mapped the Moon's gravitational field in unprecedented detail. India's Chandrayaan-1 confirmed the presence of water molecules in lunar soil. China's Chang'e program successfully landed rovers on both the near and far sides of the Moon, achieving the first soft landing on the far side in human history. These modern missions have revealed the Moon to be a more complex and dynamic world than the Apollo generation imagined. Water ice exists in permanently shadowed craters at both poles, potentially accessible to future human explorers. Volcanic activity may have continued much more recently than previously thought, with some lava flows possibly occurring within the last billion years. The lunar interior shows signs of ongoing activity, with moonquakes and possible volcanic gas emissions detected by sensitive instruments. The discovery of lunar water represents perhaps the most significant change in our understanding of the Moon since the Apollo era. NASA's L-Cross mission deliberately crashed a spent rocket stage into the shadowed Cabeus crater in 2009, sending up a plume of debris that contained substantial amounts of water vapor, along with other volatiles like carbon dioxide, methane, and traces of silver and mercury. This water likely accumulated over billions of years through comet impacts, asteroid bombardment, and chemical reactions between solar wind hydrogen and oxygen-bearing minerals in lunar rocks. The presence of accessible water ice transforms the Moon from a destination requiring complete supply from Earth into a potential stepping stone for deeper space exploration. Water can be split into hydrogen and oxygen to create rocket fuel, used directly for drinking and agriculture, or employed as radiation shielding for lunar habitats. The permanently shadowed regions that harbour this ice represent some of the coldest places in the solar system, colder than Pluto's surface, creating natural preservation chambers where materials have remained unchanged for billions of years. Modern lunar missions have also revealed the Moon's role as an archive of solar system history. The lunar surface preserves a record of asteroid and comet bombardment stretching back to the solar system's formation, information that has been erased on Earth by geological activity. Impact glass created by ancient collisions contains samples of the asteroids and comets that struck the Moon, providing insights into the composition and origin of these primitive solar system bodies. China's Chang'e 4 mission achieved a historic first in January 2019 by successfully landing on the Moon's far side, an accomplishment that required unprecedented technological innovation. Because the far side never faces Earth, direct communication with a lander there is impossible. Radio signals cannot penetrate the Moon's bulk. The mission required a relay satellite positioned at the L2 Lagrange point, where Earth and Moon's gravity balance allows stable positioning. The lander and its small rover began exploring the von Karman crater within the South Pole Aitken Basin, the largest impact structure in the solar system. The technological challenges of far-side exploration illustrate how much lunar science has advanced since Apollo. Modern missions carry increasingly sophisticated instruments capable of analyzing soil chemistry, mapping subsurface ice deposits, and studying the solar wind's interaction with lunar materials. These robotic explorers serve as scouts for the human missions planned for the coming decades, identifying resources and hazards that future astronauts will encounter. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, with the ambitious goal of establishing a sustainable lunar presence. Unlike Apollo's brief visits, Artemis plans call for building a lunar base that could support crews for months at a time. The program explicitly commits to landing the first woman on the Moon, expanding the demographic of lunar explorers beyond the white male test pilots who dominated the Apollo era. The cultural impact of lunar exploration extends far beyond the scientific and technological achievements. The Moon has inspired art, literature, music, and philosophy in ways that continue to resonate today. The image of Earth rising over the lunar horizon challenged humanity's conception of home and belonging, showing our planet as a unique oasis in the cosmic desert. The courage required to leave Earth's protective embrace and venture into the vacuum of space revealed something profound about human nature: our willingness to risk everything in pursuit of knowledge and exploration. Throughout history, the Moon has served as humanity's cosmic calendar, its changing phases marking the passage of time before clocks and calendars existed. The word month derives from moonth, reflecting the lunar cycle's role in organizing human activities. Agricultural societies planted and harvested by lunar phases, believing the Moon's influence extended to all growing things. Many of these traditional practices persist today, suggesting deep cultural connections between human civilization and lunar cycles that transcend scientific understanding. The Moon appears in the creation myths and religious traditions of virtually every human culture, often portrayed as a deity or supernatural force that governs fertility, madness, and transformation. The werewolf legends of European folklore, the lunar calendars of Asian cultures, and the moon dances of indigenous peoples all reflect humanity's ancient recognition that our lives are somehow connected to the celestial cycles playing out overhead. Modern studies have confirmed some connections between lunar cycles and biological processes, particularly in marine environments, where tidal rhythms govern reproductive cycles. Many coral species spawn during specific lunar phases, releasing eggs and sperm in synchronized events that ensure genetic diversity. Sea turtles return to natal beaches to nest during high tides associated with new moons, guided by instincts encoded over millions of years of evolution. The footprints left by Apollo astronauts in lunar regolith will outlast most monuments built on Earth. Without wind, rain, or geological activity to erase them, these impressions could remain visible for millions of years, longer than humans have existed as a species. They represent physical evidence of humanity's first steps into the cosmos, preserved in the lunar environment like fossils of our transformation from an earthbound species into cosmic explorers. As we prepare for humanity's return to the Moon, we carry with us not just advanced technology, but also the accumulated wisdom of 5 decades of spaceflight experience. The lessons learned from Apollo's triumphs and tragedies, from the patient work of robotic scouts, and from the dedication of thousands of engineers and scientists, have prepared us for the next chapter of lunar exploration. When the next human bootprints appear in lunar dust, they will mark not just a return to the Moon, but humanity's commitment to becoming a truly spacefaring civilization, one that calls multiple worlds home and carries the light of consciousness beyond the borders of any single planet. The Moon harbours secrets that continue to surprise scientists more than half a century after humans first walked on its surface. Beneath the familiar silver face that has watched over Earth for billions of years lies a world of unexpected discoveries, strange phenomena, and tantalizing possibilities that challenge our assumptions about what we thought we knew about our nearest neighbor. As we prepare for humanity's return to lunar soil, each new mission reveals that the Moon is far more complex, dynamic, and potentially valuable than the airless, lifeless rock that early astronomers imagined. When Apollo astronauts first removed their helmets after returning from moonwalks, many reported an unexpected sensory experience. The lunar dust smelled distinctly like gunpowder. This wasn't poetic exaggeration or space-induced hallucination, but a real chemical phenomenon that scientists are still working to fully understand. The smell likely results from the reaction between lunar regolith, which has been altered by billions of years of solar wind bombardment, and the humid, oxygen-rich atmosphere of the lunar module. The solar wind implants hydrogen and other elements into lunar soil grains, creating a chemically reactive surface that produces volatile compounds when exposed to moisture and oxygen from the astronauts' life support systems. This gunpowder aroma hints at the Moon's strange chemistry, shaped by an environment utterly unlike Earth's. Without atmosphere or magnetic field protection, the lunar surface has been directly exposed to solar radiation, cosmic rays, and the solar wind for its entire existence. This bombardment has gradually altered the composition of surface materials, creating complex organic molecules and unusual mineral phases that exist nowhere on Earth. Some lunar soil contains microscopic glass beads formed when meteorite impacts instantly melted and vaporized rock, creating tiny spheres that cooled in the vacuum of space. The Moon's shape itself holds surprises that contradict our perception of it as a perfect sphere. Careful gravitational measurements have revealed that the Moon is actually slightly egg-shaped, with its largest diameter pointing toward Earth. This bulge, frozen into the Moon's structure during its formation, represents a fossil record of the tremendous tidal forces that shaped our satellite when it was much closer to Earth and still partially molten. The Moon's current distance makes this asymmetry imperceptible to casual observation, but sensitive instruments can detect variations in its gravitational field that reveal the hidden topography of its interior structure. Even more mysterious are the Moon's mascons, concentrations of dense material beneath large impact basins that create gravitational anomalies strong enough to affect spacecraft orbits. These mass concentrations were discovered when lunar orbiters experienced unexpected orbital perturbations, their trajectories being subtly altered by gravitational fields stronger than the Moon's average density would suggest. The mascons likely represent the dense cores of the massive asteroids that created the largest lunar impact basins, buried beneath kilometers of impact debris and later volcanic flows, but still detectable through their gravitational signatures. The far side of the Moon continues to yield surprises that confound our understanding of lunar geology. China's Chang'e 4 mission, the first to successfully land on the far side, discovered subsurface layers that suggest a more complex geological history than previously imagined. Ground-penetrating radar revealed distinct stratification in the regolith and bedrock, indicating multiple episodes of impact gardening and possibly volcanic activity that occurred at different times throughout lunar history. These discoveries suggest that the far side may preserve geological records that have been obscured or destroyed on the more familiar near side. The lunar interior itself remains partially mysterious, despite decades of seismic monitoring by Apollo-era instruments. While we know the Moon has a small iron core surrounded by a rocky mantle, recent analysis suggests the core may still be partially molten, a surprising discovery for a world that was thought to be geologically dead. Slight variations in the Moon's rotation detected by laser ranging measurements indicate that the core is not completely solid. This finding has profound implications for understanding how planetary bodies evolve and cool over geological time. Volcanic activity on the Moon ended roughly 1 billion years ago, as the satellite's small size allowed it to cool more rapidly than Earth. But recent analysis of Apollo samples has revealed evidence that some volcanic eruptions may have occurred much more recently than previously thought. Tiny glass beads in lunar soil formed by volcanic fire fountain eruptions have been dated to as recently as 100 million years ago, practically yesterday in geological terms. These findings suggest that the Moon's interior may have remained active much longer than planetary scientists expected, with implications for understanding the thermal evolution of small planetary bodies throughout the solar system. The legal status of the Moon creates a unique situation in international law that becomes more relevant as commercial space ventures plan lunar missions. The 1967 Outer Space Treaty, signed by over 100 countries, declares that no nation can claim sovereignty over the Moon or any other celestial body. The Moon is considered the common heritage of mankind, but the treaty leaves many questions unanswered about resource extraction, property rights, and commercial activities. As private companies develop plans for lunar mining and tourism, these legal ambiguities will need resolution to prevent conflicts over lunar resources. The artifacts left behind by human lunar exploration create their own category of heritage preservation challenges. 6 Apollo landing sites contain footprints, equipment, scientific instruments, and personal items that represent humanity's first steps on another world. These sites exist in a legal grey area, while the 1967 Outer Space Treaty prevents nations from claiming lunar territory. It doesn't specifically address the protection of historical sites or artifacts. NASA has requested that future missions avoid disturbing Apollo landing sites, but these guidelines have no legal enforcement mechanism. Among the most unusual items left on the Moon are 2 golf balls, hit by Apollo 14 commander Alan Shepard, using a makeshift 6-iron club attached to a sample collection tool. Shepard's golf shots, performed in front of a global television audience, demonstrated the Moon's reduced gravity in a moment of unscripted human playfulness that contrasted sharply with the mission's serious scientific objectives. The balls, along with the improvised golf club, remain where they landed in the Fra Mauro highlands, preserved in the airless environment like unusual museum pieces from humanity's lunar adventure. The Moon also serves as repository for more mundane but scientifically valuable human artifacts. 96 bags of human waste were left behind by Apollo missions, containing biological samples that may provide insights into how extremophile microorganisms survive in the harsh lunar environment. While the waste was not intended as a scientific experiment, astrobiologists are now interested in studying these samples to understand how Earth-based life might survive exposure to cosmic radiation, vacuum, and extreme temperature variations over decades. Future lunar exploration will likely uncover even more surprising discoveries about our satellite's composition and history. The permanently shadowed regions near the lunar poles, where temperatures remain below -230 degrees Celsius, represent time capsules that may preserve materials from the early solar system. These regions may contain not just water ice, but also frozen carbon dioxide, methane, ammonia, and other volatiles that could provide insights into the conditions that existed when the planets were forming. Recent missions have confirmed that lunar water exists in multiple forms and locations, revolutionizing our understanding of the Moon as a potentially habitable destination. Beyond the ice deposits in permanently shadowed craters, water molecules have been detected in sunlit regions across the lunar surface, bound to mineral grains in concentrations that vary with the time of lunar day. This widespread distribution of water suggests that the Moon may be less dry than Apollo-era analysis indicated, with important implications for future human settlements. The discovery of lunar caves and lava tubes offers another possibility for future exploration and habitation. These underground caverns, formed by ancient volcanic activity, could provide natural shelters that protect against cosmic radiation, meteorite impacts, and extreme temperature variations. Some of these lava tubes may be enormous, large enough to house entire cities, while providing natural environmental protection. Japanese and Indian lunar missions have identified several promising cave entrances, though none have yet been explored by surface missions. Helium-3, a rare isotope deposited on the lunar surface by billions of years of solar wind bombardment, represents a potentially revolutionary energy resource for Earth's future. This isotope could theoretically fuel clean fusion reactions that produce enormous amounts of energy without radioactive waste. While fusion power using helium-3 remains theoretical, the Moon's surface contains an estimated 1 million tons of this isotope, enough to power Earth's civilization for thousands of years if fusion technology can be developed to utilize it effectively. Mining helium-3 would require processing vast quantities of lunar regolith, as the isotope exists in concentrations of only a few parts per billion. But the Moon's low gravity and lack of atmosphere could make large-scale mining operations feasible using robotic equipment. Solar-powered mining rovers could excavate and process regolith continuously during the 2-week lunar day, then use stored energy or nuclear power to continue operations during the lunar night. The Moon's potential as a manufacturing center has captured the imagination of space visionaries who envision lunar factories producing goods impossible to create on Earth. The vacuum environment and low gravity could enable the production of ultra-pure crystals, perfect spheres, and advanced alloys that benefit from zero contamination conditions. Pharmaceutical manufacturing in lunar vacuum could produce medications with unprecedented purity, while electronics manufacturing could create components impossible to fabricate in Earth's atmosphere. Solar power generation on the Moon offers advantages that make it attractive for both lunar operations and Earth's energy needs. The lack of atmospheric interference means solar panels on the Moon receive more intense, consistent sunlight than Earth-based installations. During the 2-week lunar day, solar energy could power mining operations, manufacturing facilities, and life support systems for lunar colonies. Some proposals suggest building massive solar arrays on the lunar surface and transmitting power to Earth via microwave beams, though the technical challenges remain formidable. The Moon's role as a stepping stone to Mars in the outer solar system has become central to space agencies' long-term exploration plans. Launching missions from the Moon requires far less energy than launching from Earth's surface, making it an ideal staging area for deep space exploration. The reduced escape velocity, 2.4 kilometers per second compared to Earth's 11.2 kilometers per second, means that spacecraft could be launched from lunar bases using much smaller rockets than are required for Earth departures. Lunar manufacturing could produce the propellants needed for Mars missions using local resources. Water extracted from polar ice deposits could be split into hydrogen and oxygen, the same propellants that powered the Space Shuttle's main engines. This would eliminate the need to transport fuel from Earth for Mars missions, dramatically reducing costs and enabling larger, more capable spacecraft to undertake the journey to the Red Planet. The psychological benefits of a lunar base for long-duration space missions cannot be underestimated. Mars missions will require crew isolation for 2 to 3 years, creating mental health challenges that have never been fully tested. A lunar base could serve as a training ground for these ultra-long-duration missions, allowing crews to experience isolation and confinement while remaining close enough to Earth for emergency evacuation if needed. The base could test life support systems, psychological protocols, and team dynamics under realistic space conditions. Lunar telescopes could revolutionize astronomy by taking advantage of the Moon's unique observational environment. The far side of the Moon, permanently shielded from Earth's radio emissions, would be ideal for radio telescopes that could detect signals from the earliest epochs of cosmic history without interference from terrestrial broadcasts. Optical telescopes on the Moon could operate continuously for 2 weeks at a time, without atmospheric distortion, achieving resolution impossible from Earth's surface. The Moon's low gravity and lack of atmospheric turbulence would allow construction of telescope mirrors much larger than anything feasible on Earth. A lunar radio telescope could consist of arrays spanning hundreds of kilometers, creating resolution capabilities that would dwarf any Earth-based instrument. Such telescopes could detect radio signals from planets around other stars, search for evidence of extraterrestrial civilizations, and study the cosmic microwave background radiation with unprecedented precision. Climate research could benefit enormously from lunar-based Earth observation stations. Instruments on the Moon could monitor Earth's atmosphere, weather patterns, and climate changes from a stable platform unaffected by atmospheric interference. The Moon's distance provides a unique perspective for studying Earth as a complete system, tracking global weather patterns, ocean currents, and atmospheric chemistry over long time periods without gaps in coverage. The prospect of permanent lunar settlements raises profound questions about human adaptation to life on another world. Children born on the Moon would develop in 1/6 gravity, potentially growing taller and thinner than their Earth-born parents, while developing entirely different motor skills and spatial awareness. The psychological impact of growing up under a black sky where Earth hangs overhead like a blue marble could create the first generation of humans who truly consider themselves citizens of space rather than Earth. The timing of humanity's return to the Moon coincides with technological capabilities that the Apollo generation could barely imagine. Modern computers, advanced materials, robotics, and manufacturing techniques make lunar settlements more feasible today than they were during the space race. Private companies are developing reusable rockets that could dramatically reduce launch costs, while advances in life support systems and habitat design could enable long-term lunar habitation with unprecedented safety and comfort. As we stand on the threshold of humanity's return to the Moon, we carry with us not just advanced technology, but also 5 decades of experience gained from Earth's space stations, robotic planetary missions, and the accumulated wisdom of human spaceflight. The footprints that Neil Armstrong and Buzz Aldrin left in lunar dust will soon be joined by the tracks of a new generation of explorers, scientists, engineers, and pioneers who will transform the Moon from a destination to visit into a world to inhabit. The Moon that once seemed like humanity's final frontier now appears as our first step into a larger universe. What began as a race between superpowers has evolved into a shared human endeavor to establish permanent footholds on other worlds. The mysteries we continue to uncover about our ancient companion only deepen our appreciation for the cosmic forces that shaped both Earth and Moon. while the possibilities that lunar exploration offers could fundamentally transform human civilization's relationship with the cosmos itself. And so, our gentle journey through 100 facts about the moon comes to a close. Out there in tonight's sky, just 384,400 kilometers above your head, our ancient companion continues its patient dance around Earth, pulling gently at our tides, stabilizing our seasons, and casting its silver light across the same landscapes that have gazed up at its familiar face for billions of years. From the violent collision that gave birth to both our worlds, through the patient accumulation of craters and dust, to the footprints that 12 humans left in lunar regolith, the moon's story is inseparable from our own. It has been Earth's partner in the cosmic dance that made complex life possible, humanity's first destination beyond our home planet, and now beckons as the stepping stone to our future among the stars. Thank you for drifting with me tonight through the remarkable tale of our celestial companion. Whether this journey has helped you find rest or filled you with quiet wonder at the gravitational poetry that unfolds above us each night, I'm grateful you joined me among the facts that reveal our deep connection to the cosmos. The next time you look up at the moon, whether it appears as a thin crescent hanging in the evening twilight, or a full disk bathing the world in silver light, remember the extraordinary relationship between our two worlds. Remember the cosmic violence that created beauty, the patient forces that maintain stability, and the human courage that carried our species across the void to touch another world with curious hands. Sweet dreams and clear skies. This is the sleepy astronomer, wishing you the most peaceful rest under the same moon that has watched over Earth since before life began, and will continue its faithful vigil long after the last human has looked up to wonder at its ancient light.